Alrighty, I've hit all the buttons. I think we're good to go. Maybe folks can just let me know they can see and hear me okay, and then we can get this show on the road here. Hope everyone's doing well. We can start with a few shout outs for folks that are jumping on the live chat here. If you're joining us at another time, welcome. But hope everyone's doing well. Appreciate you spending your time with us here today. Yeah, and it's almost 2 o'clock, so we might have to do keep the shout outs kind of brief. Pascal from Luxembourg, David Chapman, Loreto, Baja. Oh my gosh, I did my graduate thesis just west of Loreto, and I am hoping to go back down there next April. There's a GSA regional conference. Gabriel from Brazil, Joanne from Chesapeake, Virginia. Thanks, of course, to Susan and Amanda Jo for being our moderators today. They are the true MVPs here. Oh boy, and then a whole bunch of names just went by me. So, but I appreciate you all for being here. It's time to start the show, so I'll dispense with all the usual formalities. I tried to get on a little bit earlier, but had a couple things come up. Alrighty, so welcome to this live stream. I'm Geology Professor Shawn Willsey. Thanks for joining me. We're here as a community of learners to learn more about geology. In particular, a lot of us are interested in what's been happening this past week and even the past few years in Iceland. We're also going to look at what's been going on at Kilauea, since it's been a few weeks since I've done any sort of update on Kilauea. And then most importantly, we'll round out this live stream with some questions and answers from you. We'll try to learn together. I'll do my best to address those questions. You might have another viewer that is able to answer your question better than I can, and that's fine. That's part of the program here. No one's above anyone else. But nonetheless, thanks again for being here and joining us. If you could hit the like button, that would be great. And we'll just kind of get going here. First thing I want to let people know before we get going too far here is that you can always check out our website, willseygeology.com, for more information about Iceland, Hawaii, some of the places and locations we focus on. There's links to my videos here. I'll talk about field trips here in a second, but there's a field trip link there. We now have a store, so if you want a really cool random road cut shirt like the one I'm wearing here, you can go into our store and get some merch. And you can also, we've just started this fun little thing. If you get some merch and then you're in some cool, you don't have to necessarily be at an exciting geologic location, but if you take a picture of you showing off your merch, ideally outside, but it doesn't have to be, and then send us an email, we can feature you there. We'll have ideally we'll have a whole series of photos here of people representing the channel with their Team Willsey merchandise. Fun stuff. Hopefully you enjoy that. There's some useful links here, and all this credit goes to Amanda Jo, who's put together this amazing website. So thanks to her for doing that. You can also, if you want to support the channel, you can go into any video's video description, and there's a thanks button. If you go to any video and get the 3 buttons, once it's playing, there's a little link for thanks. Or if you can go under the video and look under the video description, there's links there for donations. You can make a monthly donation to PayPal, whatever you want to do. But this is all free, and no one gets charged anything. It's just there as an option if you want to support the cause. Okay, great. So I want to start with, I had a fun experience, I guess this past week or so, I want to share with you guys, and also make you aware of another YouTube channel that I'm a big fan of. It used to be called Ruins and Ridges, but he changed his name, his channel's name, to Luke Rockwalker. And this is a very impressive 14-year-old boy named Luke who lives in Arizona, and he does various videos. He goes and hikes up cool ridges. He sometimes looks at Native American ruins. He's sometimes looking at geologic features. Really ambitious and impressive young man. And he recently did a video and contacted me about some of the interesting things he couldn't quite figure out, or maybe he wanted a little bit more information on. And so that's this most recent video here. So he actually emailed me. I sent him some information about these bizarre cylindrical iron oxide formations he found in some sandstone near Sedona. And I was able to share a little bit with him, and he kind of shared that information I provided with his viewers on his channel. So if you want something a little bit different, maybe check out his channel. He has a nice little following. He does a great job. His cinematography and just putting together a video is way better and way over the top of what I do. So just want to give him a shout out. And I've also got a link to Luke's YouTube channel in the video description here. So if you have a chance, check that out. You might see some cool geology, you might learn a little bit. He does a great job. And maybe one day he and I can get together and do something outside in the field. That would be pretty great. Okay, so a couple other quick announcements before we get to the main parts of our program here. I do have, just related to field trips on the horizon for folks that are interested. Here we go. These are like coming up literally a week from now, so I know that's an incredibly short notice, but I do still have space next week on Friday, April 11th and Saturday, April 12th. These will be right here near Twin Falls, so maybe if you're in the region, or you know, you've got a last-minute plane ticket to anywhere, you could jump on a plane and be here. But we're going to do that April 11th trip in the Snake River Canyon, looking at rocks related to the Yellowstone hotspot, some of the younger volcanic rocks, some erosional events, Bonneville flood. And then April 12th, which is a Saturday, we will go over a little bit west of Twin Falls, and the theme there will be lava and water. And we'll look at sort of the interaction between water and lava, the aquifer in southern Idaho, evidence for large floods, not just the Bonneville flood. There's an interesting little wrinkle to the stories there at this place called Box Canyon. So anyway, there's still some room there, and if you want to sign up, you can go to the website willseygeology.com, and there's some information there about those field trips. The field trip, I guess I sort of screwed up this one here. I have a field trip on the 26th. Now I got to look at my notes. Let's see. Yeah, the 26th. That one might be close to full. It's on the website as well, but I think there might be a spot or two open because we did have a few folks that had to cancel and drop out. So if you really want to go on that one, that's up Redfish Canyon in the Sawtooth. It does involve about a 1.5 mile one-way hike, but spectacular scenery up in the mountains. Fantastic. I'll also be meeting up with Nick Zentner on probably the 28th, and we'll do a little meet and greet with viewers in Stanley that morning, and then up in Chalice that evening. But I'll put more information out about that before, maybe in the next few weeks or so, as we roll further into spring. The Grand Canyon River trip this year is full. That one's ready to go. And then I am planning to put together some field trips in the fall. I guess I sort of covered my this slide did not go well. Kind of covered my graphics a little bit here. So let me try this again. But looking to do a field trip where we start probably somewhere around Twin Falls, and we work our way towards Yellowstone, just chasing the Yellowstone hotspot, looking at all the volcanic features related to the Yellowstone hotspot and the calderas that it produced, through the Snake River Plain and ending in Yellowstone. That'll probably be a 4-day trip. I'll get information out about that once I kind of get that dialed, probably in late September, early October. And then I'll do one in probably mid-November down around St. George, Utah, Zion National Park area, southwestern Utah. Those will be individual day trips, 3 or 4 of those that you can sign up sort of cafeteria style for whichever day works best for you. The Yellowstone hotspot one, I think I'd like to try to keep that a trip where most, if not all, the participants are along for the whole ride. So just look for those coming up, and there'll be future announcements as well with regard to field trips. Before we get to the Iceland update, I recently took a trip. One of the perks of teaching at the college is you get a week in either weekend on either side of it for spring break, and we try to do something as a family each year. Of course, now the kids are getting older. Got a 24-year-old daughter, so she's kind of got her own thing going on. The 19-year-old son kind of had his thing going on. So we just had the 16-year-old boy that was stuck with us, and we traveled with another family that we're friends with down to the southern Utah, northern Arizona area. So I just wanted to show you a few photos here, a couple fun photos of the area we were in. I did make several videos down there. Normally I would already have some of these videos posted, but with all the activity this week with Iceland, that kind of trumped my ability to get some of these videos out. So look for these in the next couple weeks. So the first day I went out to this area because I knew this was a fascinating story, and I don't want to give away too much here, but this is part of the Grand Staircase Escalante National Monument. So you've got some gray Cretaceous rocks here. In fact, this whole sequence is all Cretaceous. These are the gray cliffs. If you've looked at the Grand Staircase geology or stratigraphy, kind of way out there in the distance, that's the pink cliffs. That's out near Bryce Canyon National Park. Little drone shot I did there. And then I drove in and hiked up this ridge here, and was just giddy with excitement because there's a sandstone here that's just full of oysters, and I'll show you some picture of those fossils here in a second. But a really nice sharp contact there. You can see the rocks are all dipping or tilted to the right, so very abrupt contact between the Dakota Formation and the Tropic Shale, these gray muddy rocks here. These rocks tell a very interesting and exciting story. Again, I'll wait for the video to kind of flesh that out in a little bit more detail. Here's some of the cool fossils that were in the sandstone, though. So this would be a near a coastal type of setting, and just out in the water from the beach, where there's a lot of oysters, and in this sort of sandy matrix here. So this is the Dakota Formation, which is actually a pretty common formation you can find up into Wyoming and Montana, down here into Utah. So there's some fun little fossils. Then one of the things we did down there was a lot of canyoneering. So here's one of our group members rappelling down this slot canyon, something we've really gotten into lately. You can see some of the little chip marks on the wall here of the sandstone from when this thing actually has flooding events, flash floods, and transports harder, more resistant rocks and sand that scours out and deepens the canyon. Those actually sometimes leave little nick marks on the walls of the canyon. One little rappelling photo there. Then, as most of you know, I'm a rock climber. There was a really cool climbing area I hadn't been to that I wanted to check out upstream of the Buckskin Gulch, if you're familiar with that area. And this is on the Kaibab limestone. So this is the Permian aged, about 240 million year old unit that forms the rim of the Grand Canyon. And so that's me at the top there. The fun thing I did here, I had one viewer, maybe it was more than one, but one viewer at least recently, I can't remember your name, I apologize, asked me to do a video on like climbing and geology together. And so I tried my best to do that while we were kind of here just climbing recreationally. And so what I'm doing at the top there, I've just climbed up this cliff with the camera in my hand as best I could. There was a couple spots I had to turn the camera off and use because it got a little bit tricky. But then I also did a little bit of filming from the top of the cliff. So look for that video as well. But this is a Cherty limestone that makes big cliffs in this part of southern Utah and northern Arizona. Some of you might have seen this photo I published or posted during my trip. This is the Navajo sandstone, but you can see the contorted beds here. This is something called soft sediment deformation. So basically, the beds of sand have been laid down, but they're not so these aren't really caused by tectonic forces. Usually we think of folding as, caused by tectonic forces and compression. The best model we have for these, and they're quite prevalent in the Navajo sandstone and other sandstones as well, is that these are deformed beds that were beds of sandstone that were deformed during earthquake events. So during the Jurassic, you had an active subduction zone nearby, probably lots of local and regional earthquakes, and that shaking somewhat causes those beds to sort of roll over and deform on each other, but still preserve the original bedding structures there. So really cool pattern. This was actually going down into the Buckskin Gulch. The Buckskin Gulch, if you've heard that before, is famous because it is presumably the longest and most continuous slot canyon on the planet. And many years ago, when I was a younger man, a buddy and I actually hiked the whole thing. It's close to 18 or 20 miles. We had to backpack it and spend a night at the confluence with the Paria River, and it's just miles and miles of 150, 200-foot walls above you with maybe anywhere from 4 feet to 8 feet of width there, just a few meters wide at the bottom, which is pretty incredible. So really fantastic geology there. We hiked in, but there was a lot of water in places, and our little group wasn't super psyched about wading through pools of muddy, cold water of various depths. So we just kind of got a little preview of the whole thing. The funny story with this picture here is that in preparation for this trip, I had all sorts of shoes with me. I had, my flip-flops for just chilling. I had my chacos for, doing other things. I had my climbing shoes and my canyoneering shoes and all sorts of shoes. Well, when I grabbed my chacos, I actually have 2 pairs of these blue strapped NRS chacos. And I just grabbed them thinking I had both a left and a right. And when we got down there to go on this hike, I realized I had brought 2 left chacos. So I did not have one for my right foot. And I thought, well, the Buckskin Gulch isn't too gnarly. You can see it's kind of flat. There's a few bouldery spots. I thought, well, I'll probably be okay in my flip-flops. So started hiking in my flip-flops, and it wasn't ideal, but it wasn't a deal breaker. And we ended up in a couple of these muddy spots where the water was, and that mud got on the footbed of the shoe, between my foot and the bottom of the shoe, and so it became very, very slippery. And we hiked out a little different way, like straight up the slick rock, and my foot went sideways and busted out the flip-flop here. And right when it happened, for a split second, I thought, oh, I'm okay because I can just put one of the chacos on this foot. But lo and behold, the flip-flop that broke was my right shoe, or my right foot. And so here I am with the only right shoe I had was broken, but in my pack I had now 3 left shoes. So kind of funny. So what I ended up doing was putting the chacos on, even though it was on like the wrong foot, which didn't make it fit very well. But yeah, good times. So live and learn, right? Yeah, but it all turned out fine. I also had a viewer reach out to me before the trip named Cody, and he works as a guide down at Lake Powell, where they paddle up into the lake and then up Antelope Canyon. Antelope Canyon is one of the most photographed, spectacular slot canyons. And so they paddle up into the canyon and until you run into the land, beach the kayaks, and then they hike up there. And he wanted me to come up and look at some of the geology with him. So he arranged for that. And so I want to give a special shout out to his employer, Lake Powell Paddleboards and Kayak. And there's a link in the video description. So if you're ever in that area and you either want to go on just a fascinating kayak tour with one of their guides, or if you just want to rent the kayaks or paddleboards and go for your own little adventure, you're welcome to do that. But thanks to Cody for that. So we paddled out just after first light and had just fantastic views, just these mirror image views. It was calm. The water was perfectly still and glassy. This is all Navajo sandstone here. You can see what most people call the bathtub ring. So this is when Lake Powell was at its fullest. There's a kind of a white calcium scaly deposit on that sandstone. This should all be red sandstone from top to bottom, but that's the sort of stain from the lake there. But nonetheless, it was still quite spectacular. And we hiked up the canyon. This is what the Antelope Canyon hike looks like. It's pretty flat and reasonable. It's sandy bottom. But the walls of the canyon are where the real excitement is. And in places, you can see more of that kind of soft sediment deformation in the Navajo sandstone, where you get these swirly patterns and interesting contortions in the rock, which is pretty spectacular. And then there was a couple things that Cody showed me that I wasn't 100% sure of. I think these are iron concretions, but they're kind of a lighter color than what I'm used to, and a little bit different shape. So I've got a little bit of sleuthing and research and digging to do to maybe answer some of his questions. And of course, he's interested for himself personally, but also he wants to be a better guide and be able to educate and inform his guests when he's on these trips. So really cool experience. And thanks again to Cody for putting that together. Another pictures we were kind of paddling out, just, yeah, Is it upside down or is it right side up? Hard to tell. We did another canyoneering hike that was kind of interesting because it was right by the road. This is called Cat Stair Canyon, and there's a section you hike by before you get to the first rappel where the highway department many years ago apparently took a bunch of old cars, smashed them, wrapped them. I don't know how they got them in there, but they got them in there, wrapped them with cable, and basically this is kind of like riprap because the highway is just up here. So this is obviously if you just dump rocks in here, whenever there's flash floods down here in the canyon, those can be undermined and washed out. So they tried something a little bit different, but made for a cool photo nonetheless with these older squished cars. Here's my youngest son doing one of the rappels down into the canyon. So this is the kind of thing we do when we're canyoneering. It's kind of an obstacle course to get through the canyon, and then there's like a big drop, and you've got to get your rope and harness on and rappel down, which is lots of fun, something we all enjoy. At the lower end of that, there's some pictograph panels and petroglyphs from Native Americans, which were always just fascinating and cool to look at. And then later that day we went, and I did a video here, so look for that sometime soon, of a really prominent topographic feature in the southern Utah area called the Coxcomb. Technically it's the East Kaibab monocline. That's more of the geologic name for it. So the Coxcomb is more of the topographic name, but you can see these beds of rock tilted on end. This is actually the same rock I showed you in the first photo. So this is the Dakota sandstone. We're looking to the south here. And then this gray unit here is the tropic shale. And then as you get over here towards the right side of the photo, those white beds here, the white cliffs, this is the upper part of the Navajo sandstone, which makes the slot canyons in so many areas of southern Utah. So it's fun to hike through. This is a non-technical slot canyon you can go through called the Cottonwood Narrows. So you can see how pretty this is here. And what's interesting is because the sandstone is right where the monocline is, where the fold in the rock is taking place, is this rock has been intensely fractured and fluids have moved through it. And so there's these interesting veins. You can see these veins kind of crisscrossing each other in the rock here to make some interesting patterns. So I also did a video here that I'll also try to put out here in the next week or two. There's me and the missus up at Grosvenor Arch. So that's kind of at the north end of the Coxcomb, just a very cool arch there, just south of Highway 12. The next day, which I think was our last day, we made an obligatory stop at Horseshoe Bend just to catch the cool photos along with hundreds of other tourists. It's kind of a very popular site because it's a bit of a social media Instagram kind of place. But this is the Colorado River in Glen Canyon, just downstream of Glen Canyon Dam, but upstream of Marble Canyon, which is where the Grand Canyon begins. And so you can see this cool entrenched meander where the Colorado River takes a big bend here, and it's quite the photogenic spot. Then we went down to Marble Canyon. So this is where the Grand Canyon begins. This is the Kaibab limestone on either side. This is where the Grand Canyon is quite shallow, and then from this point on downstream, it just gets deeper and deeper and wider and wider. This is there's a bridge over the river here called Navajo Bridge in the Marble Canyon area. And we did a hike. We did a hike down a wash called Cathedral Wash. So this is the wash cutting down through the Kaibab limestone. At the top of it, there's this great contact here between, this is the Triassic rocks of the Moenkopi Formation, these red mudstones and shales. And then you have that nice sharp contact with this cherty beige limestone, the Kaibab limestone. So this represents, collectively, this represents sea level dropping from a deeper water environment to sort of a tidal flat environment. This is Permian in age, this is Triassic in age. So that line right there between the two sort of spans that big boundary in geologic time between the Permian and the Triassic. And then you can take that short little hike all the way down to the Colorado River. So it's one of the shortest hikes I can think of, where you kind of start at the rim of something, even though it's a small canyon at this point, and it gets you all the way down to the Colorado River. So just wanted to share those photos with you. Kind of fun, get you maybe inspired to travel to some of these places, or at a minimum, get you to look forward to some of those videos I'll put out here in the next week or two as I try to wrangle the time to get those edited and posted soon. Okay, so those are the fun little announcements and the fun little spring break photo slideshow. Let's now switch over to our Iceland update, which I know many of you are interested in. We've had a very busy week, of course, in Iceland. I want to give proper thanks, as always, to Amanda Jo, who helps me put together this information, gathers. She does a great job of just finding stuff I would never find, both on Iceland websites and in other places, and giving me really more than I need, but a very nice, exhaustive list of resources and articles and things that I can use for these updates. Let me shrink my photo down just a little bit. Be as big. Okay, so I want to start with our good friend Isak Finnbogason, who does a lot of the drone footage when there's an eruption, and even when there's not, has posted a really great 360 image, so he can take his drone up and it splices together several images as a mosaic and then turns it into a 360 image. So here we're looking southwest towards Grindavik, and this is the eruption from this past Tuesday on April 1st. You can see these small vents that opened up just north of the January 14th eruption that destroyed 3 homes. And in the moment on Tuesday, especially when this began, I think there was a pit in my stomach. I think it was quite the sobering event initially. As the hours went on, though, it became somewhat more evident, and it felt less dire, in the sense that it was looking like this just wasn't a large volume eruptive event, and it just wasn't maybe going to have enough lava pouring out of these vents to completely affect the town in any large manner. Here's the abandoned greenhouse. Here's the protective berm that they built around the town, and swing around this way. We actually had part of the fissure cutting right through the berm, so you can see that right there. And Isak's done a great job with his footage here of an active vent, basically eroding and cutting through the berm there. Looking back up to the northeast, you can see the power plant over here in the Blue Lagoon, which were completely unaffected by this, although they were evacuated because in the moment no one knew exactly how things were going to go. But this fissure was further to the south than we expected. It was much lower in terms of total volume of lava erupted than anything we expected, especially given how much magma we had estimated was in storage. And of course, the big news here, and what actually happened, and I of course did this with my live stream and then the next day with an update, was that we mainly had an event on Tuesday that was an intrusion. So magma left the primary storage chamber beneath the power plant in the Blue Lagoon area, and much of that magma, some volume of that magma, was injected to the east and either reoccupied the former dike or formed a second dike closely parallel to it. And that extended not only down here towards Grindavik, but also well to the northeast out near the town of Vogar, and formed a dike that's up to 20 kilometers in length. And this was just the little bit of magma that was able to spill out of this highly pressurized system. And so just a nice little image there from Isak. Okay, so let's look at a couple things here. I want to go through the Met Office update and then look at the earthquake and GPS data, which I know many of you have also been looking at. So perhaps we can learn a bit together as we go over that. So let's start with today's Met Office update. Basically, the story here is that inflation, it's pretty clear based on the few days of data we have since the eruption, that inflation has resumed. So the downdrop that we saw at Svartsengi, because magma had left that body, that storage zone, and moved to the east and occupied some new space in the rock, the land deflated during that event. But in the few days since Tuesday, we have pretty clear signs that that more magma is filling that system, and the land is rising a little bit here. So I want to try to, as best we can, try to differentiate observations, facts, data from interpretations, like what it means. And, you know, because interpretations, we all maybe have our own. They're kind of like belly buttons. But the data, the facts, the observations, those are the things to really hang your hat on. But the interpretations are fun. It's fun to try to, you know, come up with hypotheses, models, explanations for the trends in the data that we're seeing. All the crazy earthquakes that we had on Tuesday, which began early that morning in earnest, those quakes are still continuing, but at a much reduced frequency than what we saw on Tuesday. And mainly those earthquakes, as I'll show you here in a bit, are happening at that far northeast end of this new magma dike intrusion area here. So further northeast than the Blue Lagoon power plant, and even further northeast than the Sunukur craters that we have seen erupt over the past year or so. And then I think the other part of their update, which is a sentiment I definitely want to echo, is uncertainty. Moving forward, everything's changed. Everything we thought we knew about this system has now changed. The magma storage zones and conduits, the plumbing system for this volcanic feature has largely been changed. And of course, we can't go down there and see it. We don't have methods to actually map or delineate or decipher how interconnected and where the conduits are, how wide they are. We don't have that ability right now, so we're using the best tools we can to try to figure out what that is. We can only estimate the volume of the magma. We can't really tell, you know, how much gas is contained in the magma, although we could probably make some rough estimates and some ranges of that. So let's go through this Met Office update, which is somewhat lengthy, but I don't want to necessarily read it all to you. You can do that yourself. But maybe just hit some of the highlights here. So they start, after they kind of have their highlights here, which I discussed, they kind of go right into the ground deformation and the GPS. And here's the main thing here. This is the Svartsengi station. So we can see that on April 1st, when the eruption began, that GPS station, which had been steadily, slowly moving to the north, that's the blue line, moving to the east, moving to the north, and really not moving at all. Like, I guess this east-west component was pretty flatlined, and then also moving up. So it was mainly moving slightly to the north and then also up during that lead up to the eruption. Once the eruption took place, it lurched and moved dramatically to the north. That's the upward motion on the blue graph here. It moved to the west, which is what we can see with this middle graph with the green dots. And then it also moved down. So we have, and we have seen this before with many of these eruptive events, is we take magma from the subsurface, bring it to the surface through some conduit, and because you're releasing pressure, you're moving volume of material up to the surface, the corresponding movement of that station is deflation. It basically starts moving back down. Each dot here is over an 8-hour period. So every 8 hours, they just measure their three-dimensional position in space, up, down, east, west, north, south. And so you can see it moving down. But what you can also see here, and I'll show you this zoomed in here in a bit, is a pretty noticeable, we don't want to look at this with just a couple data points, but at this point we have 7 or 8 data points, and they all indicate uplift. So that tells us that, well, that suggests the interpretation of that data is that we have more magma moving into the system, refilling the system, causing the land to start to swell or rise again. So that's what's happening around the Blue Lagoon and the power plant. But now that everything's changed with this larger dike, we also have to start looking at other stations further away that are moving in response to this new magma dike. So this is out near the town of Volgar to the north of the power plant, northeast of the power plant area. And you can see, you know, for the last few months, no movement, right? No movement east or west, no movement really north or south. I mean, there's some fluctuations in here, but the overall trend is pretty flatlined. But then as of April 1st, there was dramatic movement to the north, dramatic movement to the west, and uplift. and that uplift there. So that's the data. Those are the facts. Then we get into the interpretation. And one possible interpretation would be that because magma has now injected further along that dike and further to the northeast, that has caused this station to rise up because magma is moved into the subsurface. It's pushed on the rocks. It's generated a lot of earthquakes, and the land has been uplifted as it sort of swells above that magma body there. So they include those two graphs there in the Met Office update. Let's see, and then what else they have? Decreasing seismic activity, but still deformation and small earthquake activity present. So this kind of focuses on, I can make that map maybe a little bit bigger. It's a little fuzzy. It's still quite fuzzy, even though I made it bigger. But you can see the trend of the dike there, earthquakes happening up here. I'll talk about this cluster of earthquakes later, but this is the earthquakes over the past few days or so in the area. And they think that that magma body, in Icelandic, in the Met Office, they're going to call this a magma tunnel. Here in at least American English terms, we don't really use that as a term. I don't have a problem with it per se, but the more conventional term where I'm located would be an intrusion or a dike, because of its geometry is pretty much a subvertical, narrow, tabular zone of magma. But they think it's down at about a mile or 1.5 kilometers, so almost a mile in terms of depth in some places. And again, that seismicity has been decreasing. I won't click on these and make these clearer, but I think you can basically see the trend here. Here's April 1st, and each bar here is each hour of the day. So you can see the earthquakes, up to 120 earthquakes per hour during the big event on April 1st. And then those started to drop a little bit. There was a little bit of a kick on April 3rd, but since April 3rd, it's dropped considerably. This little bit of a kick here today is not so much earthquakes near the dike or what they're calling the magma tunnel. It's this other little cluster of earthquakes over here. So because it's sort of taking all the earthquakes on the Reykjanes in aggregate, it includes those as well. But the overall trend here, and the whole point of the graph, is to show that the earthquakes have been decreasing over time since the main event on April 1st. So that's all earthquakes versus time. The pink plot here is earthquake magnitude over time. So 4s are kind of at the top here, 3, 2, 1, 0, and then the negative magnitude quakes there. And you can see again that sort of relationship there. In fact, you can really see by like April 2nd, there's kind of a little step down in terms of the data there. So earthquake magnitudes dropped considerably. The kick right here, this is that, again, that cluster of quakes over in the Krýsuvík system over here. They had a magnitude, I think it was a 4 or so. We'll look at it in a second here. That happened within the last 24 hours. And here they talk about that quake, that magnitude 4 over near Lake Klevervat. We'll look at that. And then the last thing here is they have a lava flow field map, which is always kind of nice. So this is mapping out that lava pad that erupted on April 1st. So there's a more detailed map of its extent. And then shown with color here is the thickness of that lava. Near the vents, it's upwards of 4 to 5 meters in terms of thickness. And further afield, you're looking at just a few meters in terms of thickness. So, but this is the smallest eruption in volume by far of the 8 eruptions we've had since December 2023. And they do mention here, yeah, the lava flow formed during 6 hours was basically 0.23 square kilometers in area, at an average thickness of about 1.7 meters. So fairly small event that took place here on April. So turned out to be great for people in Grindavik, the power plant. So for infrastructure, it turned out great. This was a non-impact or low-impact eruption. But the big question now, of course, is like, well, what comes next? Here's earthquakes over the past day. Some offshore quakes here related to the plate boundary. Here's the trend over the last 24 hours. That's still, so we still have small quakes, mainly small quakes happening along the dike. And then there's a cluster over here, but these are undoubtedly related to just change in stress conditions caused by this magma intrusion. So that's triggering some quakes over here. There is no data to suggest that the magma is moving into this system, that we're going to get eruptions over near Lake Klevrovat or the Krishuvik system. I hear lots of speculation about those things. I'm not saying it can't happen. I'm just saying we have no data to support that. Earthquakes by themselves along a plate boundary, you should always assume, or a good assumption, is that they're tectonic in origin rather than magmatic. Okay, we're on an active plate boundary here. It's segmented. Stress on one segment can influence the earthquakes and the stress on adjacent segments, and I think that's what we're seeing here. Could we have an eruption here? Of course, and there's been eruptions there in the past, but right now there's nothing to suggest that these quakes have anything to do with the magma, or excuse me, that these quakes are related to magma that's on the move in this area. So just to be super clear there. But I know there'll be people that every time there's a little cluster of earthquakes, anywhere from the mid-Atlantic ridge, anywhere through Iceland, people get more excited because volcanoes are cool, and I understand that. So we just look at the last few, maybe look at 12 hours or so. Yeah, not as much happening, right? So there was that big cluster of quakes further back in time. That's the bulk of the quakes we're seeing there. But just over the last 12 hours on the Reykjanes, you can just see a small handful of quakes right there near that northeast tip of the dike. So they're still happening. They'll probably go on for several more days, possibly weeks. We would expect, all things being equal, those quakes to continue to diminish in size and in frequency. But this is a dynamic system, and we're not sure. We also have magma inflating the system, and so at some point things could change. But the short-term trend that's expected is a decrease in seismic activity along this trend here. We'll see if that plays out. Another way to look at the maps is with this fun website here. So right now I've got it set for kind of scope here. So here's Grindavik down here. This is the new magma dike. There's your little one, the magnitude 4 earthquake and likely all its aftershocks that happened today over here near Lake Klevrovat in the Krishuvik system. And let's see if we can let this play. So this will show you 24 hours worth of earthquakes. So boom, there's the big 4. And here comes all the aftershocks. And while these aftershocks are occurring, here's some smaller quakes happening along the new magma dike. We can also look at this just over the last 6 hours. And if you just look at the last 6 hours worth of earthquakes, you see that there's been hardly any activity over here because that was a main shock aftershock sequence. At least that's what it's looking like. Versus here, we continue to have, some earthquakes, but really there's only 6 there, right? So it looks nice with the color, but then you look at the actual data points, there's 6 earthquakes in the last 6 hours. Of course, if we go back to the whole week, then it gets more exciting, right? So if we look at the whole week in aggregate, and we can animate these and watch these coming in, but there's the southwest end of the dike that lengthened. So that dike lengthened a bit towards the southwest, just to the west of Grindavik. But more importantly and more emphatically, it lengthened the dike out here to the northeast. The stars are magnitude 3s and above. All the circles are less than 3. So let's check that out just real quick. I'm not sure how long this is going to run. So this is taking us back to March 29th. This was last Saturday. Here we are, the 30th. We're on Sunday. Got to let this roll till we get to, so a couple earthquakes happening. You can see the date here just below the stop button. Here we are now on the 31st of March, which was Monday. And then here are all those quakes coming in as we go into Tuesday, on Tuesday morning. So that's the magma breaking the rock, extending and lengthening this dike further to the northeast and to the southwest. Pretty impressive. And then what's interesting is that, and I saw this during the live stream, I still don't know what to make of it, but there were all these other quakes way out here, like 2.8, 2.4. Here's a 5. And in the moment, I sort of said, well, maybe these are all triggered by this regional stress change here. And I suppose that could still be the case, but some of these were, quite a ways away. You had some of these quakes happening, and some of these were 3s and bigger, 100 plus kilometers away. And I don't know if maybe they were real earthquakes that weren't properly located, like something in the system plotted them in some place that didn't make much sense, or if they were real. So not sure exactly what happened there, but nonetheless, we can see the main trend of the data there, which was most important. All right, so that's the earthquake pattern that we saw. I want to spend some time on this site because this shows, just to orient you, here's Grindavik down here. Here is some of the recent lava fields. Here's the Fagradalsfjall eruptions from 2021 to 2023. The yellow lines, I think, are, so I can look and see. Oh, except it's in Icelandic. That's these are like faults or structures. In fact, most of these blue lines or yellow lines are some sort of structural lineament. Could be fractures, could be faults. So you can see sort of the regional pattern there. But more importantly, what we're after here is all the blue dots are the GPS stations. And the GPS story now has changed considerably. In the past, over the last year or so, we've been focusing, right in this area because this is where the magma body was. And we've been looking mainly at the Svartsengi station because that's kind of told mainly the story that we've been looking at over this past year. There you go. So there's the past year. Each one of these red lines that drops, that's an eruption. There's the May 29th eruption. There's the August 22nd eruption. There's the November 20th eruption. And here's this last eruption out here. So that's the station among the stations we've been focusing on because that's the area above the magma body. And as the magma body, that magma storage zone has filled with more magma, we've seen it inflate and deflate correspondingly. But now, because we have this new event, this intrusion that pushed magma through the rocks in the subsurface up to about here, and also did it a little bit to the southwest as well. Now we also need to look at some of these other further afield stations because they also reveal what the magma, how much magma moved and how much the ground has shifted because of that magma intrusion. So if we come over to this station here just to the east of the town of Vogar, we can see, and I guess I can make this bigger. That helps. Zoom in a little bit. So this is this station. We'll start at the top. So here we are. This is for, see, this is the last 3 months. So here we are in February, March, January, February, March. It's not moving. And then suddenly, April 1st, there's pronounced northward movement of this station. Middle graph shows east-west movement. No movement. April 1st, intrusion. Dramatic movement to the west. So north and west, so we have northwest motion. And then our up-down graph, not really anything going on. And then movement to upward movement. And not just one upward movement that then flatlined, but based on just a few data points, which by no means is totally conclusive. We have 3 data points that are still trending upwards. So that's what that data shows there. If we go to, and remember that one was to the northwest. I wanted to do a vector map for this. I wanted to put arrows on all these stations showing which way they moved. I just didn't have time with getting tests from the testing center. Anyway, whatever my day was like, I just didn't have time, so I apologize. So remember that station moved to the northwest. So if we go over here to this station, which is a few kilometers to the east, let's see how this station moved. Head and look at it bigger. In. So here's this station over the last few months, up and down, but really not moving, right? There's just a net, not much movement here, some error bars on these. But then it has downward movement. And on this first one, north-south, that's southward movement. Then we come to the middle graph, not really moving. April 1st comes along. It's a little subtle here, and it's not totally demonstrative, but maybe looks like there's some downward movement here, which would be a little bit to the west, but really not much movement, but definitely some movement to the south here. And then the last one, which shows up and down motion, you can see the kick here of it moving up. So we have that motion there. Let's look at another one on this side. Let's look at this one here near Kilauea, which I know a lot of folks are interested in as well. So this one looks much more compelling. So we're missing some data points here for whatever reason, but again, last 3 months, north-south movement, not much, and then downward movement on this graph is to the south. So this station moved to the south. We go to the middle graph. Upward motion on this thing is to the east. So in aggregate, we have southeast motion. And then we can see the upward motion as well on this third and final plot. So going back to the map, getting rid of that. Again, I wish I could draw the arrows on here for you, but what we have here is over here, these stations are moving to the northwest. Over here, these stations are moving to the southeast. When you come out to this station here, this seems to be beyond, and we know that the earthquakes kind of stop right about here. They didn't progress this far. So presumably the tip of the magma dike or intrusion is somewhere in this zone. It didn't go this far out. And sure enough, if you go out to this station, there's not a whole lot to look at. No net north or south movement for the most part. Really nothing moving in terms of east-west. And a little bit of an uptick here, but it looks like it's had some up and down. You know, it's within the range of the background noise anyway. So this one does not show demonstrable movement at all this far to the north. So before we get too worked up that, you know, the dike's headed for the capital or something like that, we don't see any movement in the GPS stations out here. But definitely if you come into these, if I did the same thing here, I'll spare you the whole analysis. But if you look at these two stations, you'll see the same sort of pattern. So that dike is more or less paralleling these existing structures. Notice there's a little bit of a change in the trend here. It's a little bit more steep here, more south versus west. But as you come up into this area, it changes to a little bit more west-east component. It's kind of bending in that direction. And that's right on line with the dike. So the dike is the magma pushing through the rock. It has located and found some of these existing structures in the subsurface, forced its way through those structures, probably widened those fractures with the pressure of the magma. And by widening those fractures and breaking the rock, that generated all those earthquakes that we saw on Tuesday, and those earthquakes we still are experiencing to some degree even today. So the GPS information here is getting interesting because in previous updates, I just kind of focused on this area. I was always looking at other ones too, just for the sake of the update. I didn't want to show you 20 different GPS plots, but moving forward, we're going to have to focus on two places. We're going to have to look at the primary magma storage area, which we know sits here. And now we're also going to need to look out in this direction to see what's happening over here. Does the uplift rates here correspond to the uplift rates here at the same time? That would seem to indicate that both magma storage zones, if they're inflating at the same time, that shows a clear connection and that the magma is filling them both up at the same time. Is there a lag between the two? Maybe this fills up first and then we see it happening over here. Right now, according to at least a couple days worth of data, which is short, that's small sample theater for you, it looks like we have magma that is still accumulating and pushing into this northeast zone. And we're still getting earthquakes there. So it could be just, a little bit of pressure, gases, whatever, that's pushing it in that direction. We don't see any evidence that the magma is moving upwards. So right now, there does not seem to be any evidence that the magma that's moving underground still is going to come to the surface and force an eruption. That could happen down the road, but right now there's no data for that, data to support that. I didn't have as much time to look down here, but we also want to look down towards Grindavik because we know we also had a earthquake swarm that occurred at the southwest end of the dike, and it'd be good to look at these as well and see what the trends are there. In fact, let's just do that real quick. I didn't have time to do this before the date, but why not, right? So here's one just to the west of Grindavik. You guys can see the dots here. You know, it slowly was moving southward, but boom, there's the earthquake, and it moves dramatically northward. It moves dramatically westward, so northwest motion, which is what you would expect on that west side of the dike, is that it's going to get pushed to the northwest. And in this case, it's downward motion. So this could be the formation, could be part of the Graben structures right above the dike, perhaps. We'll have to see. And so I do have a graphic that kind of goes with that. So remember, when these dikes intrude like this, we typically get the area straight above it because the dike is sort of forcing the rocks laterally out. So it's pushing the rocks apart. See with the big arrows here, tension. And that usually occurs because what happens along with that is that the rocks immediately above the dike, there's some subsidence there. And so we get these faults, these normal faults on either side of it. And so if we can figure out, if we have enough data from the GPS stations, we can oftentimes figure out exactly where these faults are, because we can look at the GPS stations that have dropped or subsided here. We can also look at the INSAR data for that as well. But this is a graphic I've shown before, and that's one that's particularly instructive. Okay, so yeah, I don't want to spend like an hour on the GPS plots. Keep the show moving as much as I can, but also want to provide good amount of information for you. So I'll make sure this is, once we wrap up the live stream, I'll make sure this website is in the video description if you want to look at any of this stuff here. Okay, I was going to also show you just the regular GPS plots, but I think we've looked at enough on the map view. It's the same data that we don't necessarily have to go through those. But you can start to see some of these, right? Like figure out where these stations are. You can see many of the stations in the area have a notable change in all three directions, north, south, east, west, up, down, right at the April 1st event. If you see stations that have no change without looking back at the map, those are likely ones that were too far away. Like here's Lake Klevervatten right here, no change. So before we get too excited about the earthquakes over there, the GPS doesn't show any movement at all. So the ones that are affected by the magma movement will be the ones within that, you know, few kilometer region of that new dike. The INSAR data shows this nicely. So here's the latest INSAR data. The white dashed line here more or less delineates the location of the dike. Some of these other white lines are the fractures that have opened up down here near Grindavik. Presumably there might be some fractures. There already were fractures out here anyway. I don't know if they've actually mapped new fractures that have opened up or maybe reactivated fractures. But all the little fringe bands here on the INSAR data nicely shows exactly, you know, how much it moved. And so each one of these colored bands here is several centimeters of movement. So you can see there's been in aggregate quite a bit of movement. And this is just from the 31st of March to April 2nd. So two satellite passes 3 days apart, and you can see considerable movement there on the INSAR data. Good stuff. All right, moving on. Talk about Kilauea. So samples were taken of the lava that happened, the eruption from Tuesday, and so there's some preliminary analyses from those samples. So they've looked at the petrography and the geochemistry of those, and without reading this to you, basically it's very similar. Here's this data point right here, and this data point right here is the April 2025 eruption. And so you can see in terms of magnesium concentrations, it's plotting in the same range as all the other eruptions. In terms of potassium versus titanium, it's plotting in the same place as well. And so not much new. It just looks like it's the same batch of magma. It's not some new or primitive type of magma. It's more or less the same batch of magma that we saw previously. And here they say this shows there's been no significant change in the conditions of magma storage since the onset of these events. The other thing they have here is a fun little photo micrograph of showing the crystals in it. And you can see these tiny little needles. These are tiny little plage crystals, but then there's a huge one here. And so these larger crystals would be crystals that formed when the magma was sitting underground for maybe months or so at a time, cooling slowly. Those crystals grew large, and then they were incorporated in the actual movement of the magma to the surface, erupted at the surface. And so you've got these big crystals mixed in with these small ones. There's gas bubble in there, big olivine crystal kind of in here, but these long needle-like ones are plagioclase feldspaths. So make sure that link shows up in there as well. A couple news items that Amanda Jo sent my way. This one just talks about the dike propagation to the northeast formed a graben, a down-dropped depression. Basically, this thing here is what we call a graben, a fault-bounded subsidence feature. So they've actually documented that. The news article, a little bit about that there. There's another one here. This one talks about the cracks in Grindavik. They've mapped all the fractures and cracks in town. Some of them have been kind of repaired and filled in. Others are still open. Still others, actually, there were some that widened or new cracks formed on Tuesday when we had this intrusion event. And yeah, so there's a map down here that shows you the town, there's the harbor, and where some of these cracks are, some of these major either faults or fractures. Some of these, of course, formed way back in November 2023, but then some of these, I think most of these are from 2023, but there's some new ones maybe from this past Tuesday, and or some of these maybe widened or shifted a little bit during all the earthquakes this past week. Another article here focuses on the road, and so with this new intrusion, which kind of goes out to this area here, now we now have something new. The new sort of setting that we now have to face and kind of think about and deal with is we've had magma from about just north of Stora Stokfelt down to near Grindavik in the subsurface since November 2023, but we now have magma in the subsurface, as shown by the earthquakes and the GPS data, that extends out to at least about here, somewhere in this area here, just northwest of Kilauea. And so with that magma out there, they've got to think long and hard about this road here, this highway between the airport and Reykjavik, which is called Reykjanesbraut. This roadway here, there's definitely a threat and a hazard here to the infrastructure of this road, not to mention this town of Vogar here. And so this article just speaks to the fact that they're used to, if that roadway were to be covered with lava, they could probably reestablish a road within a few days after the eruption ends, and they would figure out through different routes and stuff how to get people to the airport. They've got some options there. There's other roadways, to the south through Grindavik and other places there. Apparently, according to what Amanda Jo's been able to find, there is not any plans that she's aware of to build any sort of defensive berms around Vogar or the roadway. And really, the roadway would be a particular challenge because it sort of parallels the slope here. If you did have eruptions here, so likely that if it covers the roadway, they're just going to let it cover the roadway, go where it goes, and then try to reestablish the roadway as soon as possible, recognizing they've got some other roads and options here in the area. But apparently that one of the places that they had proposed for a new airport was either here or somewhere in this little swath here was a place they were looking to build a new regional airport, and that may have to be revisited in light of what's taken place this past week. And then winding down this Iceland update, there is I'll also put this, Amanda Jo sent me this great image that I'll share with you guys as well once we wrap up. having spent the last year plus, getting used to and familiarizing ourselves with some of the topography and features around Grindavik, now it feels like we also need to look a little further to the northeast. And so this is a kind of a nice view. See if I can get you guys oriented. There's Grindavik there. Here's Fagradalsfjall. This probably was taken in 2022, maybe 2023. You can see what looks like a little bit of volcanic gases coming out there. But this labels a lot of the prominent hills in the area. So here's the power plant, Stora Stogfelt, Kilauea, the big kind of prominent hill on the Reykjanes is here it is over here. It's kind of cone-shaped mountain here. Now we're looking towards the northeast, towards Reykjavik there. Anyway, the nice 360 shot that shows some of the terrain, and you can zoom in on it. It actually points out some of the topographic features here. Apparently this is a older shield volcano out here. Well, I will try to pronounce that because it's good practice. Steinskjaldbron. I butchered. Skjaldar. Oh boy. Okay, and then there's Vogar over there. And then a paper I did not have time to read, but apparently it's actually not even technically out yet. It's slated for May 15th. Really want to read this one. I'll put links in the description, but it looks like it's open access to anyone. Of course, it doesn't include what happened this week, but it does talk about inflation, deflation cycles at Svartsengi and repeated dike injections and eruption in the Sunukur crater row. So completely relevant to what we have going on. A whole host of scientists collaborating on that, including some names we know, Iceland, like Benedict Ofik. So I'll give that a look-see here sometime soon. Okay, let me switch gears now and now take you from a volcano that's complicated and has a lot of uncertainties and is leaving us scratching our heads and wondering what's next. Let's switch to a volcano that, at least for the last few months, has been behaving kind of nicely and somewhat routinely overall, and that is Kilauea. And so I haven't done a Kilauea update in 3 weeks or so, so let me just do a brief one here, and then we'll turn to you, good folks, for any questions you might have. So here's a live view of Kilauea right now, and I haven't done anything with this for a couple weeks, but I have been watching. So even though I haven't done updates, I have been kind of paying attention to what's going on there, and it's been doing some spectacular things. Basically, we have these eruptions that began December 23rd of this past year within the Halemaumau crater. So all the lava is confined. This is not a hazardous situation for the most part at this point. And we have had a series of eruptions. We're up to now, I think the one that just ended yesterday or so was episode 16. We've had this somewhat cyclical, although it hasn't followed a perfect pattern, set of eruptions that now has produced 16 individual eruptive events, including 1 or 2 eruptions ago, there was lava fountaining up to 1,000 feet, about 300 meters, which is pretty spectacular. And the tephra, the little pieces of lava blown downwind, have really started to accumulate on the west side of the crater, and even some of it's accumulated a bit here and there to the northwest as well. But all the lava is contained within the crater. So let me provide a quick little overview. So here is the road coming in to the park. So the visitor center's over here. There's a restaurant hotel called Volcano House. This is the Kilauea military camp. This is also where the new USGS Hawaii Volcano Observatory is being built. It's right here. The old site was out at the end here. Assuming the conditions are good, you can actually drive out to these overlooks. And the 2 vents that have been producing the eruptions, there's a north vent and a south vent, just 2 side-by-side vents over here on the west wall of the Halemaumau crater, which sits within the greater Kilauea caldera, this bigger depression out here. So that's sort of the location where all the action's been taking place this last few months. if you're getting confused with all these episodes and when they begin and such, like I am, they've actually got a nice handy dandy timeline. So when each episode started, here's episode 1, when it started, date and time, how long it lasted, and then how much time it took until the next one started. So basically episode 1 went for 14 hours, and then 16 hours later, Christmas Eve, we had episode 2, Christmas, so on and so forth. And they've got this almost completely updated. They have episode 16 ongoing, but actually it's over now, so they need to update that. But you can see the different episodes that took place there. Of course, I was able to be in Hawaii for, I think it was episode 8 or 9. No, I can't. One of those two when I was over there with the group. The latest update from the USGS on Kilauea is episode 16 just ended on April 2nd at noon. The summit reservoir is now reinflating, so we're just setting the stage for another eruptive episode that might begin within a week or so. 16 episodes with various degrees of fountaining separated by pauses in activity. Let's see, we'll look at the monitoring data here in a second. Fountains and lava flows have erupted from 2 vents, referred to as the north and south vent. Each of the episodes lasted from a few hours to over a week and were accompanied by strong deflation of the summit region. So it's going through this very somewhat predictable inflation-deflation cycle, at least for the past few months. Some of the cool images out of the USGS. Let's take a look at some of the fun pictures they've taken. Let's go first to this one. I think is really cool. So here's one of the USGS scientists at the rim. So that sort of line right there, it drops down about 400 feet right there, and that's actually the lava fountaining sticking up, extending above the crater rim, which is pretty remarkable. When I was there, the fountaining wasn't even quite to the crater rim. It was maybe 2/3 of the way up or so. And since that time, some of these fountaining events have become more dramatic and higher, maybe kind of a nozzle effect. Maybe the conduit's a little bit restricted, maybe a little bit more gas-rich gas component in the magma. So a nice photo there. And then you can see the brown stuff here. This is all the tephra. So downwind of this lava fountain is where all the fine, frothy pieces of airborne material is falling. A couple other images that kind of caught my eye. Let's see, this one here. And so much tephra has accumulated on that west side of Kilauea that it's starting to not only just bury the landscape, so there's actually a landscape of lava flows and little mini canyons and stuff here, but signs. So this says Southwest, it should say Southwest Rift Zone. If we read the caption here, this sign used to stand at least 6 feet or 2 meters above the ground surface. So this just gives you a bit of a marker as to how much of this airborne tephra falling out of the sky has accumulated just since about Christmas time. Pretty impressive. And then finally, couple here. Let's see what I want. Oh, this one here, again, I think the tephras, so there's some of the fountaining in the crater. You can actually see the color change here, right? You can actually see the faint roadway here, this little structural feature here. But all this light brown is all the tephra, and it contrasts pretty markedly with the black lava down here in the crater. So all this material has been blown by the wind and the fountains and accumulated out here on the west side. And one more picture that's similar to that. Yeah, just kind of another picture there showing just how much of that tephra is accumulating there. Crunchy stuff. Some of the videos from the USGS. This one's actually pretty cool. This is the first 13 episodes of the eruption in time lapse. So we're going to go back to December 2024 and very quickly show the cyclicity of these 13 eruptions. So here we are with episode 2. Here we come. So 3. I probably will lose count here, but this just kind of shows you the the progression of these things. These vents started out low at the bottom of the crater floor, but have built up over time. You can see some of them sloughing off. So as the fountaining occurs, you can see some of them collapsing. But they've also built up quite a bit of tephra material on the backside here. So these ones weren't particularly high in terms of fountains, but we'll see some of the bigger ones here as we roll into February and March. There's some higher fountains coming out of these. Now we're into, yeah, there's some high ones there, March 11th. And that looks like, yeah, it only goes through the first 13, but thought that was pretty cool. And here is the other interesting thing that these vents have been doing is something called gas pistoning. Basically, like concentrated slugs of gas-rich lava have, when it's not fountaining, have caused the vent to rise and somewhat fall like a piston. And so this nicely shows that behavior. So there's the lava kind of welling up, but then it kind of drains back down. And then it kind of wells back up, pushes that lava up like a piston, and then it kind of drains back down. So when it's more gas rich, it's rising, and when you have more lower concentrations of gas, it drops. That's sort of the explanation for that. But that's the new term for, at least the term they've been using for this, gas pistoning. And there's some papers written on it. It's this cyclical lava vent behavior of down. Another time lapse. This is from episode 14. This was March 20th. It will show you this phase of the eruption. Work out of the USGS to capture this. Here we are, March 19th, morning. Get this eruption going. They're sort of calling it the eruption begins when the lava like leaves the vent area, when it actually pours out or shoots out high enough that it's leaving that immediate area. So you can see some of the lava pouring out here. Base. We are in the afternoon. It's kind of doing this pistoning thing, but we've come to learn that that precedes the high fountains. So we should get to some high fountains here as we go into later portions of this cycle. Some of that lava is removed and more of the gases can contribute. See some of the lava filling out. Here we are at night, 7 o'clock at night. Wait for it, it's coming. Lava spilling out. You can see that pistoning behavior out of both vents, both thing, gas pistoning. Hope I got the right video clip. I do. Oh, they've all had fountains. Oh, it looks like it's getting a little more vigorous. A little more vigorous there. That's the north vent on the right. Vigorous. And, you know, just like fireworks, it's got to end with a grand finale, right? So, this thing going. Next day in the morning, now they're both, there you go. Ta-da. Crazy through the early hours. North vent kind of shuts down. South vent still going. And then show down. Vent there. Gasp. Yeah, the show's over. There you go. Then you start building it up for the next one. That kind of is nice overview, kind of how that works. 2 more videos, and then we'll wrap this up here. Let's see, this one here is episode 15. This was March 29th, so this was just within the past week or so. And this is another time lapse of the fountaining, just so you can kind of see the behavior. This is just one vent. Kind of seen this. Here you go. This was the one. So this was the one. Notice that the fountaining goes beyond the frame of the camera. This was the 1,000+ feet, 3+ meter fountaining event. This is the highest one so far. Basically twice the depth of the crater was how high the lava fountains were. You actually can see some direction. You can see it moving back and forth, a little bit change, I guess, with the wind, maybe a little bit of slight change in the direction. coming from the vent. Mainly that looks like the south vent was doing the work on this one. A little bit of rise and fall coming out of that north. Good stuff. Great show. Job, Kilauea. Paying for the National Park Pass and getting in the park and seeing the show. And then the last one here is, this is the most recent one. This was from Tuesday. So while we were all fixated on Iceland, Kilauea was also trying to grab our attention with some of this activity here. And here's a nice helicopter overflight from episode 16. So while you were all watching what was happening on the Reykjanes, Kilauea was putting on maybe a more spectacular show, just not as threatening, I suppose. But had that been happening just north of Grindavik, oh boy, that would have been grim indeed. South vent there, fountaining well above the rim, tephra accumulating on the downwind side, a little bit of lava kind of oozing out of there and dribbling down. But continuing to fill in, partially fill in this very large crater. This will accommodate quite a bit of lava. So the near term, we don't need to worry about this too much in terms of hazards, although the tephra can be a little bit of a hazard regionally and volcanic gases can be a bit of a hazard. But as long as the trade winds are somewhat reliable, that should kind of keep things at bay. And then to wrap this up, just some of the monitoring data at Kilauea. So this is our tilt meter. So this is showing as this trends upwards. This goes back to the last month or so. As this trends upwards, the ground is swelling. It's upward movement. And every time it starts to go down, that's the beginning of an eruption. So I think this is episode 13, episode 14, 15, and then the most recent one, 16. So basically, once this thing trends back up over the next few days and gets kind of close to this threshold, you can see all 4 of these last eruptive events have hit a pretty similar threshold in terms of the tilt, the microradians of tilt before the eruption began. The USGS is now using that as a crude tool to estimate these kind of probability windows when the next eruption might take place. The GPS data this looks at across the whole caldera. You can see this goes for the whole year. So you can see since December of 2024, it's pretty much been stagnant. So there really hasn't been any extension or movement across the caldera, which I think indicates you've got no more magma coming in than is already taking place there. So it's sustained, I suppose. And then lastly, this one adds in a few other little wrinkles here. So here's the floor of the crater. Each one of these kind of steps is an eruptive event. So here's an eruption here. More lava pools out onto the crater floor, raises it up. Another one here around March 11th. This little downward turn is probably because the lava is losing gases, so it actually deflates a little bit. And then I'm assuming this little kick here, I don't know why this doesn't go up to today. This would be the most recent eruption. So no, this would be 15 because 16 was here. Yeah, I don't know if I need to research or whatever, but you get the idea. Earthquakes, and there's been a few clustered around here, but nothing really changing for the most part. So the big question I guess I would have about Kilauea would be, when will this cycle change? Like, are we going to see these repetitive episodes playing out for the rest of the year? How long into the future? And I suppose, it's really not likely to change unless you get changes in the rate of magma influx. You might get changes in gas concentrations that might cause the behavior to change, or more likely, the thing that's probably more likely to cause an abrupt change in what we're seeing there would be earthquakes, or the eruption itself changing the conduit, changing the stress conditions. If the conduit widens, if the magma finds an easier pathway somewhere else within the volcano, then that could change the location of the vent and the eruptive style completely. So a little bit there on Kilauea. Hopefully that was helpful to you. This was kind of a long-winded update. It was a lot of Iceland stuff to get through, so thanks for hanging in there with me, folks. I have not even glanced at the live chat since I started. Literally almost 90 minutes ago. So I'm going to take a quick drink of water and catch my breath and see what questions you folks have. Thanks again for being here. Make sure you hit the like button. Thanks to Amanda, Joe, and Susan. But let's see. Yes, I have questions from Amanda, Joe, at least some preliminary ones. So let's start with some of these here. I'm guessing we're going to have a lot of questions on Iceland, but we might have some on Kilauea or some other topics as well. From DJI Mini 2, I think some time could be spent on the interpretation of the latest INSAR, various scenarios it might show, and the complexity in interpreting and deciphering horizontal from upward motion. Yeah, definitely. I hope we touched on that enough. I hope we hit that to your satisfaction, but we did spend some time looking at the movement at various GPS stations here, and also looked at the INSAR data as well. It's definitely gotten a lot more complicated. We've typically had just this one bullseye, just a couple stations reflecting the movement into the main storage zone, but now we have this secondary dike. So this is as complicated as it's been since November 10th of 2023. Let's see. Other questions in here. Earthquakes yesterday around Kilauea and the Krishuvik system. So let me address this really quick because I think this is important. There are on the Reykjanes and throughout Iceland, almost every topographic high point you look at, and even some low points, right? There's fissure systems like the Elverp system here. Volcanoes are everywhere in Iceland, and Kilauea is one that people gravitate towards because it's steep, it's cone shaped, it looks like a volcano. Like you just look at that landscape. If I asked some random people getting off the airplane in Keflavik, like, show me the closest volcano, a lot of them would point towards that. And while those volcanoes have erupted in the past, the potential for those volcanoes to become reactivated by what's taking place now is really low. And here's why. I mean, if you look at it, there's dozens, I mean, more than that. There's maybe up to 100 different volcanic vents and features on the Reykjanes Peninsula. And it's different than in central Iceland, where we have like big central larger volcanoes like Hekla and Katla. What we have here, we have smaller volcanoes that are kind of, for the most part, what we call monogenetic, meaning they just erupt once, meaning they form a conduit. A magma's in the subsurface, there's a conduit formed, it erupts for some period of time. That might be one eruption, that might be a few hours like we saw on Tuesday. Might be sustained eruptions from that one location that go on for years potentially. But eventually, when that eruption ends, that magma in those conduits solidifies, it hardens, and if there's more magma in the future that forms, it's likely to find a new path upwards. So there's really no reason why this magma is going to move towards Kilauea, which has solidified magma in its subsurface, when there's all these fractures and weak ground and easy pathways to form a new volcano. So we're much more likely to see something here. In terms of the Krishuvik system, yeah, it's still kilometers away. I mean, we're skipping the whole Fagradalsfjord system. Why aren't we considering? We're much more likely, I think, right now, if maybe something pops up here versus here. But for now, we know where the magma is to some degree, and we have no evidence that the magma is moving into some other system. And until we see that data, and that data would not just be earthquakes, it would have to be ground deformation and earthquakes. And right now, are we getting earthquakes over here? Yes, but these are mainly tectonic quakes, and we should assume as such. So the question is, the magma jumping systems? No, the magma right now is staying in this system. So that's one question folks had that Amanda Joe sent me. Another question folks had, will it erupt in Grindavik eventually? I mean, it could, right? We know the magma dike runs through or is very close to parts of the town. Their second question was, why are they trying to let people move back when the ground is still opening up? They're trying to play the difficult game that I certainly don't want to play, of giving people personal freedoms and not over-regulating this. So those who've chosen to sell their homes have done so. Those that are choosing to live there can, for the time being. You know, you can't stop people, I suppose, from making some of these decisions. It's tricky. It's messy. I don't want to probably talk too much about that. But is there a hazard here? Could it erupt in Grindavik eventually? Yes. I mean, right now we've got towns surrounded, got the ocean on one side, and it's somewhat surrounded on 3 sides by lava that's erupted in the last year and a half. Doesn't mean that the town's going to be covered in lava, but until we see signs that this whole system is abating to some degree, then we have a significant risk there. And I think the public officials are trying to do their best to manage that, let the businesses there, like Papa's Pizza, operate during times between eruptions and let people kind of live their lives. And then also when an eruption is imminent or taking place, like we saw on Tuesday, it was evacuated and people were warned and they got out of the way. So it's tricky. I definitely wouldn't want to be the one in charge of making those calls for everyone. Okay, some other questions from you folks. Jimmy Hamilton, the 3 GPS stations within Grindavik show significant subsidence since the activity on Monday and appear to be lower than at any point during the last 3 eruptions. Is this positive news for the town? No, I think the GPS stations that maybe went down, I'd have to see which one. They might be related to these grabens. I think those are more tectonic in nature. Remember, right above the dike, you can still get downward motion. So it's very likely the magma is still here in the subsurface. We just might have some of those stations within that graben where the downdropped area occurred. So is it positive news for the town? I don't think so. The positive news for the town was they dodged another bullet on Tuesday and lava did not go into the town. And beyond that, it's just sort of day by day and kind of waiting to see. From 2 fathoms deeper, the swarms that happened a couple of weeks ago now seem as a warning as to what was about to happen. Note from Andy, not a question, but can you... Yeah, I mean, we might have been seeing some of those quakes as sort of precursors. I mean, the magma might have been breaking a little bit of rock, causing micro quakes at either end of the system. And then on Tuesday, there was like a big break, and it was a bit of a domino effect, right? So there was a bigger break, bigger earthquakes. Magma rushed it forward, propagated through the crack. That put more pressure on the leading edge of the crack, maybe widened out the next segment, generated more earthquakes. And again, a bit of a domino effect there that I think we're still seeing to some degree with even today, with smaller earthquakes and less frequent earthquakes, but it's winding down, but it's still taking place. Email question from Sue. Looking at the uplift graphs on both Quake 2.0 and near real-time 8, I'm not familiar with those. Both show a sharp shift to the northwest on the Svartsengi sensor. Doesn't usually do this, does it? And although there are not enough data points to say for sure, it does seem to be showing a rapid uplift again. We're looking at something totally different from what happened before. Do you have any guess what has changed? I think I didn't see if I just open. She maybe is on some site. So let's go to the Svartsengi here. So a sharp shift to the northwest. Yeah, so I can see that there. So let's actually go, let's try this. It here. And yeah, now we're looking at it for the whole year. That bigger. So you can see here, each time we had an eruption, it moved north, but then here it moved south, and then it moved south, and then it moved north. Here it's a little bit more regular, and then it's moving west, it's moving west, it's moving west, it's moving west. But the north-south movement is a little bit more convoluted. It could be where that GPS's location is with respect to the magma body and sort of the central bulge, right? Like if in one eruption, maybe it's like, you know, off to one side of the apex of that bulge, if you can think of it that way. So during that eruption, it shifts one way, and then maybe during inflation in the next cycle, maybe the bulge in the magma system is in a different spot, perhaps. That's just me spitballing some ideas. Did I answer all of your questions? Not enough data points to say, but it seems to be showing rapid uplift again. Yeah, I've only got a couple data points there, but I think we saw that on the other one here, that you definitely got a, oh, base is probably, there you go. More of a, that's pretty rapid. I mean, look at the trend here, and the uplift there is much more rapid. Could be, I mean, there's a lot of different things that come to mind. Doesn't necessarily mean, it would be odd for it to be produced by increased magma coming up from the deeper zone, like influx rates increasing after we've seen months and months and months of uplift here. Could also be just sort of the elasticity of the rocks, and you've changed everything. There's been a down drop, and so initially maybe we get rapid uplift, and then it starts tailing off a little bit as we go forward in time. Yeah, good questions. You guys are on top of it. Sharp group here. Back to stuff. Okay, next question. Just trying to get to as many of these as possible. If I don't adequately address your question, apologize. $3D modeler from Rotterdam. Where are the turbidites in Iceland when I can see them clearly in Hawaii? Are you talking about turbidity currents and the deposits from turbidity currents? Those like kind of continental shelf slope avalanches? Yeah, sort of. I don't know if that's what you're talking about, or maybe you're referring to something else, but it feels like a little bit off topics. Apologize for that. Gabriel Ferreira, with the, do you think this last event in Iceland was another rifting event, like November 10th, 2023? Absolutely. So I wouldn't call it a rifting event. That's probably not the verbiage I would use personally. I would call it an intrusion. We had a large magma intrusion. We also had one March 2nd of 2024, but it was small, not very large. But this is the biggest one since November 10th. Your second part of your question, Gabriel, is will it open space for more eruptions in different spaces on the Reykjanes Peninsula? Well, it certainly, I think, is opening the options for having, I mean, anywhere where the magma is in the subsurface, you can get that magma moving up towards the surface. So instead of kind of focusing on a narrower zone from just north of Stora Stokveld down towards Grindavik, now we have a longer magma storage zone adjacent to the larger storage zone. Remember, we have two sort of things here. This is, think of this storage zone over here as, I know we call it the magma chamber, but it's, and I've drawn this before in older updates, it's not a blob of magma, even though on a lot of graphical representations we're going to show it as such. It's little levels, think of like a honeycomb kind of thing, like a lattice of magma stored in the fractures and the cracks. The magma is going into places and spaces where it can. And here in Iceland, we have spaces and weak zones between different units, horizontally, stratigraphically, and also vertically. Probably this like weird horizontal, vertical, interconnected lattice that's in here. Now, if it stays there long enough, you can, if you have enough magma coming in, it can slowly but surely start to partially melt the rock in between, and maybe it starts to amalgamate into something bigger. But then that magma feeds into now, and has in the past, this much longer and more extensive storage zone that's a dike. So this dike is oriented vertically, different than the storage zone, which is more horizontal. Sills are for storage. This is a fun little saying in volcanology. It's not 100% true, but it's generally true. Sills are for storage, dikes are for transport. So dikes are what move the magma either towards the surface or laterally along strike. And so getting back to your question, we have a lot more space in the subsurface to put magma. So it's probably going to take more magma influx to fill that space to trigger an eruption. That being said, on Tuesday, we had a little bit of magma come out, but a lot of it moved through the system. So the question moving forward is how much more magma can accumulate here before it produces enough pressure to inject into this system and possibly cause an eruption? Or instead of an eruption, does it just lengthen further? Does it just, is the tip of this area and this rock out here in the subsurface so weak that it pushes forward into this area? And with earthquakes, we would see that, of course, and just make the whole magma dike longer. And it potentially could do the same thing at the southwest end out here off the coast. From Hans van der Niet, with the second eruption near Grindavik, was this more like a pressure relief and it became small because the biggest chunk of lava suddenly moved more north? Maybe. That's a good, I mean, I don't know for sure, but obviously the system, even though magma moved into the new dike system, moved out, at least partially moved out of the storage zone, despite making more space for itself with that injection or intrusion of magma, there was some overpressurization. The magma found a little pathway out to the surface north of Grindavik, so you could call that, yeah, pressure relief. From Lars Edblom, how long can the lava stay molten in the dike? It's a really good question. Rock is a really good insulator. One of the, and I've heard this from other people too, but one of the reasons why we didn't maybe see a lot of rock breaking earthquakes in this zone between like Hagafelt and Stora Stogfelt. This is the area we thought it was going to erupt in, right? This is where most of those past eruptions had taken place, was in this zone here. But one reason why perhaps we didn't see a lot of activity is the magma that's in the subsurface in this central section is partially solidified, and magma can get to a consistency. When it's hot, it's runny and it's mobile and it can move. When it's completely solidified, it's stiff, but it can be broken, right? It's brittle. But in between those two end members, magma can be stiff enough that it can't flow, but not stiff enough that it can be broken. It's in this in-between sort of consistency, and it's possible that this magma that was left down there in that middle part just was of that consistency, and that's why we didn't see a lot of earthquake activity or other things taking place. It was the northeast and southwest end that was more, it was the main player there. So how long can it stay molten in the dike? The dikes too are, and I think I saw the Met Office put out, they're only about 1 meter wide, so they're not that wide. So you can figure you've got 1 meter wide zone of magma that, now it's still a lot of magma, right? Because it extends laterally, you know, forwards and backwards for several kilometers, and it extends downward for several kilometers. So it's still a large volume, you know, millions of cubic meters of magma, but it's only 1 kilometer wide, and so it's touching the wall rock on either side of it, and it's cooling from that contact point in. I would say it takes probably decades for it to completely cool, but probably less than that for it to be molten enough to continue to flow. So to answer your question, how long can the lava stay molten in the dike? Assuming it's a 1 meter dike, I would guess a good ballpark number might be, and this is just guessing, maybe a couple of years. It's molten enough to still be movable magma. Jan Clancy, if the uplift is higher than before, could it all happen more quickly? Maybe. I mean, I guess, are you asking like the eruption could happen more quickly if the uplift is higher? You know, we haven't moved this rock. This rock has just now been deformed for the first time in a long time, right? So all this rock up here has now had magma being injected into it. That's what's causing all the earthquakes. The stress conditions are different, and it's presumably moved up, perhaps because this magma has been injected into it, and that's caused it to move outwards, northwest and southeast on either side, and upwards a little bit. Then Niemi, couldn't the magma intrusions and the earthquakes be part of tectonic lateral extension of Iceland? Absolutely. So the tectonic forces are the ones that are the big players, right? They're the dominant control on things over the long term, certainly along this plate boundary. But in the short term, since November 10th, 2023, we know magma has filled some of those fractures related to the tectonic extension. And so the magma is the main driver in this region over this short time frame. But bigger picture, absolutely. So the magma and the earthquakes are following tectonic created structures, faults, fractures, as part of this divergent extension or this divergent plate boundary. Wolfgang Grieb, what are your thoughts about the higher uplift rate? Do you think the conduit between the magma chamber and the dike is sealed now? I think it's too early to say. I don't know. I think the interesting thing now is going to be watching the data in the next weeks and months to come and see how the GPS data, I mean, we've only got a few data points since this whole thing changed. And so it's just too soon to say for sure. So do I have any thoughts? Not really. I just want to watch the data before I make any sort of interpretation. Kava, Canum, is there any way you can show the 3D seismic data to show the possible progression of the magma body? Well, the magma body is no, because the only thing, the seismic data isn't necessarily delineating the magma body as an outline. It's just showing us where rock is breaking, and some of that rock is breaking because magma is forced upon it, is being injected into it, and some of that seismic data may be farther afield, like, you know, a few meters away, tens of meters, hundreds of kilometers away. Those stress changes from that magma injection, those rocks breaking. So I'm not sure. I totally get your question, but we don't have the tools or the resolution to basically outline the shape and morphology of the magma body, or to actually see it moving. I don't think we have those tools, if that's what you're asking. Deep Skyall, as the magma chamber fills, will the magma in the intrusion act like a liquid and seek a common level up the northern end? Well, it's not a liquid. Magma is not a liquid. It is partly a liquid. It's molten rock, but it also has crystals, so there's solid component to it, and there's gases in it. So it's actually all three phases of material in the magma, and the composition of each one of those three phases will dictate to some degree how it will behave. If you have highly gas-rich magma, it's very buoyant. If you have it's very molten and liquid, it's easier to move through places. It flows well. If it has more of a solid component to it, if there's more crystals, it's crystal rich. It's more sluggish and goopy. We sometimes call that even crystal mush. So will it seek a common level? I don't know quite what you mean by a common level up the northern end. It will take the weakest path that it can find. So if it can continue to propagate through fractures and stay in the subsurface, it will. If it becomes more gas rich, it might become more buoyant, and then it maybe starts moving upwards. So we'll have to wait and see what happens there. Steffi Adcock, are there any fault plane solutions, beach balls, to analyze for the recent Krishevik earthquakes to see which way the stress is being directed? The site we use for the earthquakes doesn't show. They used to have those, but to my knowledge, we can't see those anymore. So I've no doubt that the USG, or excuse me, that the Met Office likely has those still, but I don't think so. But sometimes we get quakes that are big enough that they get picked up by the USGS, and so we could look at these quakes. I mean, these are not the ones you're asking about, but these quakes, sometimes, if they're big enough, we sometimes get fault plane solutions or beach balls for these. So here's a 5.2 on April 1st, just northwest of Grindavik. Click on that one. That one might be big enough we get a beach ball. Let's see. There you go. So use your beach ball analyses there and figure that one out. Just kidding. I'll tell you what it is. This is a normal, this is an oblique fault, so it's normal and strike slip. It's either a north-south trending fault or an east-west trending fault. And to be honest, it could be either one, because across this part of the Reykjanes, we do get, we do have some east-west strike slip structures that kind of link a lot of these sort of more north-south trending structures. So given that it's strike slip, if I had to guess without knowing the geology there, I would guess it's this east-west one, but maybe not. Yeah, so to answer your question, yeah, I don't know where that data is for the Krishuvik earthquake. If someone knows and wants to share that with the team, that would be great. Vivid Magic, I keep wondering about the 800 to 1,000-year intervals between the 300 volcanic events in Iceland, 300-year volcanic events in Iceland. And logic tells me we're at the beginning. Do you agree with that? I don't know. I mean, we rarely, all volcanoes are different, and none of them, I can't think of one volcano that has this like perfectly cyclical, oh, every 300 years we get an eruption and it lasts this long. What we often do is we calculate recurrence intervals just based on averages, right? So you might have like 7 events, and the average between events is, 300 years or whatever the time component is. But that means that sometimes there's a lot more time and sometimes there's less. That being said, the very limited data we have on the Reykjanes is that it has shown, at least with those last 3 eruptions, that there is some crude cyclicity. I guess I could pull up something that might help here. Simple graphic. Straight. Computer's working time here. I don't know. Maybe, I mean, the fact that we haven't seen anything on the Reykjanes for a long time, for several hundred years, and now we've got this period of activity, it would appear as if, yes, we are at the beginning of one of these cycles. But, would I put my salary down and say 100% for sure we're going to go through 300 years of on and off eruptions? I don't know, but this is the data I was talking about. So the yellow bars are volcanic eruptive events based on what we know from the geology and dating those eruptions. So there are sort of 3 cycles of this. Is 3 cycles enough to hang your hat on? I don't know. Maybe not. So, but clearly it's different now, right? There's been several hundred years of quiescence, and now there's more activity here. The million-dollar question to me is what's controlling that? What's causing, what's changing across the Reykjanes where every couple hundred years the conditions are right, that now magma is influxed into all these systems and erupts for a few centuries and then goes back to sleep for a while. Really good questions there. Which I had the answer. So do I agree with it? Not necessarily, but I'm open to it. Seagull, what is the future of eruption, whether it is last eruption or it will continue in that region? Maybe what is the future of the eruption, whether this is the last eruption? Maybe that's what you mean. Lead into that question. I don't think this is the last eruption, but it could be. But we still know, we know after 3 or 4 days of data that it looks like magma is reinflating the storage system. And we know that magma will ultimately, if it continues, and it's been doing this for a year and a half now, move into this magma dike. And you can only store that magma for so long. So do I know 100% for sure we're going to have another eruption? No. But is the chance quite high? Would I advise people in Iceland to be ready for another eruption? Yes. Where? Somewhere between this point and this point, most likely. And when? Sometime in the next year or 2. Like, just still so many unknowns. Lars Edblom, do you think they will add GPS stations in the Northeast? Yeah, that's likely, given this new data trend. We know after the the November 10th event, that more GPS stations were added down near Grindavik. So you can see the density of GPS stations here. So I wouldn't doubt, yeah, I'd like to see another 5 or 6 stations scattered throughout this region up here. So yeah, I would guess that would be something they're considering. Terry Leah, could the peninsula turn into an island to the west? I don't think so. So you want to take the whole peninsula and rip it apart and inundate it with water. Not likely to happen. The lava is spilling out of these regions on the peninsula at a greater rate than the extension caused subsidence, and so that builds up the land. So I think our past is a good indicator of what the future there. Maddie N, there's a gap between the southern portion of the new dike and the northern portion. There's some sort of blockage in between where the gap is. Yeah, maybe that's what I was talking about earlier, like where there's this the middle section there might be different magma consistency. Maybe there's something different in that section. Not quite sure. Ethan Simone, why didn't the magma come out of the area which has weakened crust due to past events, but they rather went too far nearby main highway? So we thought it was going to come out here because that's the pathway it had been taken for these prior eruptions. But again, we hadn't seen an eruption since last November. And so it's possible that this magma had just become a little too sticky and gummed up and just, just wasn't hot and mobile enough. And the magma pressure building up here couldn't really move it either. And so it propagated to the northeast and southwest and found fresh rock that was broken and could be exploited and broken further with those earthquakes and filled in that space with the magma. That appears to be just one interpretation of what happened. Lots of questions here, team. This is great. And I've got another one to get to. Oh, boy. John Sykes III, when does a dike become a pluton? Oh, boy. So a dike is a subsurface magma body that cuts across layers of rock. It's typically vertical or at a steep orientation. It's usually fairly narrow, so it could be as thin as, a few centimeters and as wide as maybe 100 meters would be at the big end. To be a pluton, you would need that magma body to change shape. So you need to continue to accumulate magma, partially melt the surrounding rock, and create more space for that magma body and just basically create a blob. But plutons, I'd have to look this up. Plutons have a specific size requirement. And so an intrusion to be at the pluton scale would need to be much, much bigger. So when does a dike become a pluton? Probably after a long time, hundreds of thousands of years, maybe millions of years of magma accumulation and assimilation of the surrounding country rock. And then to us geologists who have definitions for these things, it needs to be a certain size. And I can't remember the area or the volume required for a pluton, but you could probably look that up. Really fun question. Bart Rivers, the last uplift from Svartsengi appears to rise faster than before the April 1st eruption. Yes, I noticed that too. It may be too early to draw conclusions on that. I would agree. It is too early to draw conclusions. It's like 4 data points, but let's go anyway. But I wonder what your thoughts are on that. Could be just a rapid rebound of the ground, maybe some elastic rebound. The ground fell, you bring in more magma and it's able to maybe move up, because remember, as it's accumulating before the eruption, its elasticity typically slows down, and so we get less uplift then. It could also be higher rates of recharge. Maybe magma left that system, and now that pressure has been released, that's allowing more magma to move up into that shallow storage zone from depth. Yeah, those are my thoughts on that. I don't have a complete answer for sure. Chip Hall, are the older cinder cones, here we go, Hawaii question, are the older cinder cones from the Kilauea eruption in 2023 completely buried in lava, or are they partially buried? I think they were more like spatter cones, weren't they, in the crater there? And I don't remember off the top of my head exactly where they were located. So I think they were further to the east. I would guess, well, Chip, I don't know 100% for sure. They probably are not completely buried. They might be partially buried. If they're the ones I'm thinking about that are further to the east in the on the crater floor, I think they're still sticking up, and because they're sticking up, the lava's flowing around them. I'm not 100% sure. All right, I got a couple more Kilauea questions, and then I'll switch back to these Iceland ones here. Joanne Kellum makes great hats. With lava accumulating in the Kilauea crater, does that impact how they measure inflation? Do they start measuring at the new top of the lava? Well, the inflation isn't isn't measured. I've been doing this too long. The inflation there is not, it's different than how we're measuring it in Kilauea or in Iceland. They're measuring it with a tilt meter across the whole caldera. So basically, as inflation, as more magma moves up in the system, they're detecting that as a tiny tilt, an angle change at the surface. Reading your question right. Accumulating in the crater, does that impact how they measure inflation? No, but then they are measuring the floor of the crater, which is rising and somewhat falling with more lava that's added to it. So as more lava is added to it, that raises it up, but then that lava can lose some gas. It sinks a little bit. It can also subside a little bit as you're just stacking up all this heavy, dense rock. Hopefully that worked, Joanne. Hope I got your question. Aaron McGee, is the pistoning you showed at Kilauea a similar mechanism to the very first eruption at Geldingeldur? I don't remember that one well enough to know if that's a good comparison. That first 2021 eruption, I was paying attention to Iceland, but not as strongly as I did the next year with the Meraldia eruption in 2022. So I'm claiming a little bit of ignorance on that eruption. But if it looks similar, then it might have been a similar process. Kava, wasn't it the case in Hawaii 2018 that there was old magma in two places from the old eruption it came to the surface in? Yeah, so if you're referring to when the first lava erupted down in the neighborhoods of Leilani Estates in the lower East Rift Zone in late April or May of 2018, when they analyzed that magma, they found that that was old magma that was in the subsurface. It was pushed out by that fresh, hot magma. Those initial eruptions in Leilani Estates were just goopy and they didn't flow very far. And then later, once there was a clear conduit established and that fresh hot magma could get through the system, then those lava flows were very fast moving, much more forceful with gases, and a much bigger hazard. So that eruption really got going by like May and into the early part of June. Back to Iceland questions. Given the low effusive volumes, this is Karen Robertsdotter. Given the low effusive volumes in the Grindavik end of the fissure, both on April 1st and last January, is a reasonable interpretation small southern sills connected by a choke point to the rest? Yeah, if I'm reading you right, Karen, maybe there's a small magma storage zone that feeds those southerly eruptions that's connected to the larger body, but not connected well, maybe through a narrow conduit, something like that. That's possible. And that's the trick, is we don't know what the subsurface geometry looks like. We don't know what the plumbing system looks like. We didn't know a year ago, and now we really don't know. It's become larger. It's probably become more complex. And so that's the difficult thing with figuring out where an eruption might take place, what areas to focus on, because we have three sort of hazard zones. We have Grindavik itself at the southern end. We have this central zone, which is a hazard to the power plant in the Blue Lagoon. And now we have a northern zone, which presents a hazard to Vogar and Reykjanesbraut, the highway here. So I think there's sort of three hazard zones moving forward based on infrastructure. And until we get closer to that next eruption and start looking at the data, right now it's a crapshoot. Like right now, if you said, where's the next eruption going to take place? I have no idea. I could say, I could convince myself that this northeast end where all the earthquakes were and the magma just moved in, that's where the action is. That's the likely location. I could maybe wake up the next morning and talk myself into, these conduits that were established this past year being the likely location. And then on a third day, I maybe could make some arguments for this southern zone near Grindavik being the location. Another question from Chip Paul: is it safe to say perhaps the magma chamber or chambers in Iceland look kind of like an ant farm? Yeah, that's a pretty good analogy. Now imagine, an ant farm is still largely two-dimensional between those two pieces of glass or plexiglass. Now imagine it being three-dimensional, like a lattice, and that's maybe a better view or rendition of how that would look. Yeah, it's kind of hard to 3D image it in your brain, but that makes sense. That's a good analogy. Vivid Magic: is there any insight into the strength of both magma chambers? That's an interesting question. Yeah, we talk about, well, you can definitely study rocks from a tensile strength viewpoint. Engineers do that all the time. What we can say is that the main magma body underneath the power plant Blue Lagoon area, for whatever reason, the rocks above that magma body seem to lack a lot of pathways or weaknesses that allow that magma to move up vertically. That's why it would make sense that if this is where the magma body is, the vent and the volcano should start and erupt somewhere in here. But instead, there's a pathway from this magma body to the east that feeds this weak zone, this Sunakur crater row that's existed for hundreds of years. And this weak zone is the preferred path. So I don't know if we can say how strong the magma chamber is. The magma is only, the strength of the magma is probably not the thing to consider. The thing to consider is the strength of the rock that surrounds the magma chamber. That would be something I'd want to know. Like from the southwest tip near Grindavik all the way up to the northeast, are the rocks that surround this dike of equal strength, or are there differences? Where is it weak? Why is it weak? What are the pathways? What's the geometry of the fractures that make it weak? Even though this is all basalt, we've talked before about that there's a lot of differences in the strength of the rock. Some of these lava flows are gas poor. Some of the rock in the subsurface could be old magma that's solidified underground, so it's very dense. It didn't have gas bubbles in it. It formed underground under pressure, so it's very dense and compact. Other places in the subsurface, we might have lava flows that erupted at the surface thousands of years ago, or erupted underneath a glacier, and they've got pore spaces and pockets, and there's pillow lavas and hyaloclastite and all these different rocks that can form in this environment that might be very weak in terms of their properties. Camilla Cox: how do they know the dike is only 1 meter wide? I'm not sure with this specific one, but I mean, you can go around Iceland and see dikes in all sorts of places, older dikes that have been, that have cooled, crystallized, and are now exposed in rock faces. There's a really cool couple of cool ones here on the Reykjanes I take people to. There's one down here near the tip that you can kind of walk to that's not even a meter wide. It's probably like a third of a meter wide, maybe 20-30 centimeters wide. It's much more narrow. I'm not sure off the top of my head how they estimate the width of the dike. Maybe from the INSAR data. Good question how they know this specific dike is 1 meter wide, but it's definitely within the right kind of ballpark. And remember, these fractures are starting out not very wide, maybe just a few centimeters. The magma is pushing into those fractures, forcing the rock apart. So now that fracture has doubled its width, and in doing so, that forceful injection of magma has just broken the rock, and that's generated seismic energy, and there's your earthquake right there. But very good question, Camilla. I'll have to, I feel like I somewhere in the dark recesses of my brain I know that, but I can't recall that at this point. Kenny Clark: could there be a several kilometer long fissure? Could the entire dike erupt along the whole length? Is that even possible? I suppose it's possible. I don't know if that's ever happened, where you have a subsurface dike of a given length and you eventually get to a point where it erupts and it splits along the whole length of that dike. It wouldn't surprise me if that's happened at some point in the past, but my guess is that the more common event would be a partial rupture along some segment or section of the dike. D Lane, how far from the surface are the magma chambers? And do they know the appropriate dimensions of the chambers, or how many are associated with this volcanic region? Well, we know this dike here, we read in the Met Office update that this magma body is about 1.5 kilometers down from the surface. The bigger, well, the main zone down here under Svartsengi is like 4 to 5 kilometers down. So it's feeding this dike, but it's at a deeper level than that. So good stuff. I answered. That's a lot of questions, but we had a lot to cover there, friends. That might be the longest question answer session I've done in a while. We're about 2 hours into it, so I'm thinking we should maybe wrap up. I know there's probably more questions in the queue there that I didn't get to, and so we can try to capture those next time, perhaps. Is that okay? This has been really awesome, though, so make sure you like the live stream. I try to do these. My goal is to do at least one a month or so. I mean, I'm not perfectly scheduled with these, and it just kind of depends. Like we had the Eruption Tuesday, and certainly if something like that happens, I want to jump on and try to live stream and learn and experience that event with you as best we can. We were able to use Nature Eye, go up in the drone and get some images. Thanks to them. I do have links for Nature Eye under the video description if you're interested in getting a drone up in Iceland with Johan and flying over this brand new lava field or any other area there around Grindavik. I'm sure they would be happy to help you. Big shout out again to Amanda, Joe, and Susan for helping out with the chat here and moderating. For those of you over in Europe, it's probably getting kind of late, so I want to thank you for joining us today. Love our community. We've got a great group of folks here. Continue to monitor this, as I will, and feel free to share your information with us, and we'll do likewise. We'll just have to see moving forward. I would guess that sometime next week I would get another Iceland update out. We'll see what happens with Kilauea. I did email Mike Poland from the USGS, the director of the Yellowstone Volcano Observatory. He's over in Hawaii right now doing a gravity survey, but he would love to jump on a live stream with our community again in the next month or two, so I'll probably set something up with him. I'll get some of those videos out from southern Utah, northern Arizona from my trip. The Geology 101 series is not done. I know that I haven't done any new ones in quite a while. There are still several more lessons, mass wasting, rivers and streams, groundwater, glaciers, desert processes. I just haven't got to those yet. So if you're a big fan of the Geology 101 series and you think it's all done, hang in there. It might be till summertime before I can circle back to those, but I will get to those again soon. And I've got some other interview series videos hopefully coming out soon as well. So yeah, good stuff, team. I'll go back through the live chat once we get this wrapped up and try to look at some of this. I hope some of the things I was able to share here was helpful. I've mainly been talking to my screen and my camera for the last 2.5 hours or so, and I haven't been able to see what you folks have said or if those explanations have been good. So let me know. Hopefully the communication was effective and engaging, and we were both able to learn from each other, because that's the idea. That's where it's at. So we'll go ahead and sign off. Have a great weekend, or perhaps it's already Saturday where you are. Enjoy the spring or the fall, depending on the hemisphere you're in. Looks like great weather here in southern Idaho. Try to get out and get some rock climbing in tomorrow. Otherwise, I'll be in the office working on all sorts of other things, including grading tests. Semester, we have like 5 weeks left in the semester, and it's the busy time for sure. So good things are happening, though. All self-inflicted fun. I'm not complaining. So thanks again, everyone. Appreciate your time with the live stream. Thanks for your support of the channel. And thanks for all you do. We will see you guys next time. Take care. Be well.